In the last lecture, we applied Gauss theorem to several situations. We applied Gauss theorem to a uniformly charged conducting sphere, a uniformly charged non-conducting sphere, a uniformly charged shell, a line charge, a sheet of charge, all those situations. And now, we have chosen a few examples which are based on Gauss theorem, so that the ideas that were expressed in Gauss theorem and in all these situations, they get fixed up. So, let us take a few examples. Example 1. In a certain region of space, uniform electric field is given by this: E equal to 3 I cap plus 4 j cap minus 8 k cap. I think you remember that I cap, j cap, k cap are unit vectors in the x, y and z directions respectively. Find the electric flux through a surface of area 12 units lying in the x z plane. So, if I choose x, y and z, then the plane is x z plane. That means, the normal to this plane is along the y axis. So, the surface lying in the x z plane must have its normal along the y axis. So, the surface has area S equal to 12 j cap units. You see, remember, the surface area is a vector and the direction of this vector is normal to the surface, which is j cap. So, surface area is equal to 12 j cap, and now I find E dot S. So, E I have got, S I have got. So, I just take the dot product, and in the dot product we remember that I dot j would be 0, k dot j would be 0, and the only thing left would be j dot j, which is equal to 1. So, 4 times 12 is 48. So, 48 units of flux. Let us take another example. A hollow cylinder has a charge q coulomb within it. There is a charge q coulomb within this. If phi is the electric flux in units of volt meter associated with the curved surface B, find the flux linked with the plane surface A, not both of them, but A. But you remember, the whatever flux is linked to C must also be linked to A, they must have equal amount. And what is that flux? That is the total flux q by epsilon 0 minus the flux through this surface, which is phi. So, the flux through surfaces A and C is q by epsilon 0 minus phi, and since these surfaces have equal area, therefore, the flux through any one of them is half of that quantity. So, the flux through A or C is half q by epsilon 0 minus phi. Example 3. Given that the electric flux through surface S1 is n times that through the surface S2, find the charge Q4 in terms of the charges Q1, Q2, Q3 and n. So, the situation is this: we have a sphere which encloses charges Q1, Q2 and Q3. We have another sphere which includes not only these charges, but also charge Q4, and we are asked to find out the charge Q4 in terms of the charges Q1, Q2 and Q3, if the flux through S1 is n times the flux through S2. Now, what is the flux through S2? It is Q1, Q2 plus Q3 plus Q1 divided by epsilon 0, and n times that must be equal to the flux through the surface S1, which is total charge Q1 plus Q2 plus Q3 plus Q4 divided by epsilon 0. And from this equation, we can find what Q4 would be in terms of Q1, Q2 and Q3. It is very simple. The result is that Q4 is n minus 1 times Q1 plus a Q2 plus Q3. Note that if n is equal to 1, Q4 is equal to 0. If the flux through this sphere is the same as flux through this sphere, obviously Q4 must be 0, because it has not contributed anything to the flux through S1. This is a very tricky situation. We have a cube here, and the charge q is placed on the corner of the cube, and we are asked to find out the flux through the farther surface of the cube, through this surface. Now, how do we do that? The charge is not inside, the charge is placed on the corner. So, what do we do? What we do is, we embed this charge inside a cube of twice the side. We erect 8 cubes instead of 1, and now this charge is inside this. You see, I have shown this dotted surface of the earlier cube and the charge is here, and now the charge is inside. Therefore, the flux through all the sides of the cube would be equal to q by 6, because there are 6 surfaces all equal in area. But now one surface is equal to 4 times the surface of the original cube. Therefore, the total flux through this side is 1/4 of q by 6. So, it is q by 24. Let me repeat this, the charge is here, it is not inside. Therefore, we made it inside by erecting this cube, which is twice, whose side is twice the side of this cube, and now the charge is inside. The flux through any side is q by 6, any side is 4 times the surface area of any side here, and therefore, 1/4 of q by 6, q by 24. So, q by 24 by epsilon 0 is the flux through this side or any side. So, as another example, we take two concentric thin spherical shells of radii a and 2a, and they are uniformly charged. The inner one carrying positive charge q and the outer one carrying the negative charge minus q. And we have to find the electric field, the direction of the electric field at the point P, which is inside the inner shell. Now, what do we do? Inside the inner shell there is no charge, because the charge is only on this surface and on this surface. Therefore, inside the field is 0. There is no charge. If I erect a spherical surface inside, then 4 pi r squared times E would be equal to 0. Therefore, E is equal to 0. So, inside the inner shell the field is 0. So, at point P the field is 0, the direction is irrelevant. Now, we take the same thing, two concentric thin spherical shells of radii a and 2a, and again uniformly charged, the outer one carrying a charge minus q, the inner one carrying a charge plus q, and again we want to find what happens at the point P, which is now within the two shells. Earlier it was within the inner shell, now it is between the two shells, the point P is between the two shells. So, what do? We draw a Gaussian surface through P, and what happens? Inside this surface the charge, the outer is outside this surface, therefore, it does not contribute to the charge, only the inner one contributes the charge, and that charge is plus q, and the sphere has, if it has radius say this, then it will be 4 pi r squared times E equal to plus q by epsilon 0, because the outside charge does not matter, because it is not inside the Gaussian surface that we draw. So, the field is only due to the charge on the inner shell, and that charge is radial, as we found in the last lecture. So, at the point P the field is in this direction, radial from the point or from the center of the two shells. So, it is this in this direction, not in this direction, not in this direction. The charge is positive, therefore, the field points radially outwards. Same thing again, but now the electric field at the point P, which is outside. So, same exercise. Now, the point P is outside the two shells, and what happens now? If I draw a Gaussian surface through P, then what happens? It includes both the shells, and the inner shell has charge plus q, the outer shell has charge minus q. Therefore, the total charge inside this Gaussian surface is 0. Therefore, there is no field at the point P. 4 pi r square times E is equal to 0, because there is no charge inside. Therefore, E is equal to 0, and therefore, once again the direction is irrelevant. The field at the point P is 0. All right, let us modify this now. Again we have two concentric thin spherical shells of radii a and 2a, same thing, but now the inner one carries a positive charge which has sigma per unit area, and outer one has charge minus sigma per unit area. It is not the total charge given, it is the charge per unit area which is given. Then the electric field at the point P, say again we take the point P outside, what will happen? Again we draw a Gaussian sphere. What is the charge on this? It is 4 pi into square of 2a into sigma with a minus sign, and on this shell it is 4 pi a squared into sigma. So, the total charge would be the 4 pi a squared into sigma minus 4 sigma. The outer one carries a larger charge because it is a larger area. So, it is 4 pi a squared into sigma minus 4 sigma. So, the net charge is negative. If the net charge is negative, then the field at the point P will point inwards. So, in this case the field will be pointing inwards, radially inwards, because the negative charge is larger in magnitude than the positive charge on the inner shell. All right, let us take a slightly different case. The charge density inside a non-conducting sphere of radius a varies as rho equal to k r, where k is a constant. Show that the magnitude of the field inside and outside the sphere are given by these expressions. We shall find them. Let us see the situation first. We are given the charge density inside a non-conducting sphere of radius a. So, this is the sphere of radius a, and the charge density is not constant, but a function of r. How do we find the charge then? You remember in the last lecture I told you how to find the charge inside a sphere. We take a shell of radius dr. The area of this surface area of this shell is 4 pi r squared times dr gives us the volume of the shell, multiplied by the volume density, that gives us the charge inside the shell. Then we integrate from 0 to a or 0 to r or whatever the radius, and we get the charge inside that sphere. So, we take a spherical shell of radius r and thickness dr, as I have been saying, and the charge dq inside this shell is 4 pi r squared dr, that is the volume into the volume charge density, that is rho. And what is rho? Rho is k r dr, and k is a constant. So, it becomes 4 pi r cube dr into k, and k is constant. So, it goes out, we integrate this and we get 4 pi k r 4 by 4. So, any sphere of radius r inside this will have a charge which is 4 pi k into r 4 by 4. And from Gauss theorem, since it is a spherical surface, the field is all radial, normal to the surface. So, 4 pi r squared E is equal to 4 pi k r 4 by 4 divided by epsilon, and therefore, E inside is, if 4 pi gets cancelled and r squared and r 4 leaves only r squared. So, we get k by 4 pi epsilon 0 into r squared. So, the field inside now is proportional to the square of the distance from the center. Now, for a point outside, the whole charge is inside, and what is this charge? This charge again, remember this, we can draw a shell, and this is 4 pi r squared k r dr, that is the charge. And now, if I integrate from 0 to a, I get the total charge. So, if I integrate from 0 to a, we will get 4 pi k a 4 by 4, that is the charge inside. And again from Gauss theorem, 4 pi r squared E is equal to 4 pi k a 4 by 4 divided by epsilon 0. So, therefore, E outside is k a 4 by 4 pi epsilon 0 into 1 by r squared. That is interesting, because whatever happens for points outside, the whatever charge inside behaves as if it is concentrated at the center of the sphere. So, therefore, it is 1 by r squared, right. So, the field outside is 1 by r squared, and you can calculate the total charge and so on. So, the field outside is k a 4 by 4 epsilon 0 into 1 by r squared. Now, we take a slightly different case. A thick spherical shell has inner radius b and outer radius a. So, it is a thick shell, therefore, inner radius b and outer radius a. This is the shell. The density of charge in the shell, not inside the shell, in the shell here, that varies as k by r squared. And now, we are asked to find the electric field at points outside the shell, and also inside the shell for a point at a distance r from the center, which is between b and a. So, it is inside the shell. The shell is thick. So, let us find out. The first thing is to find the total charge in the shell. What is the total charge in the shell? Again, now I will take a spherical shell 4 pi r squared times dr is its volume, and I will multiply this by the charge density, which is k by r squared, and then I will integrate to find the charge on the shell. I will integrate between b and a, not from 0 to b or 0 to a, but between b and a. That will give me the total charge on the shell. So, the calculation is quite simple. This charge on the shell dq is 4 pi r squared rho times dr. Rho has value k by r squared and r squared cancels. So, we have 4 pi k dr. Thus, the charge in the given shell is the integral from b to a. So, it is 4 pi k integral of dr, which is r and limits from b to a. So, it gives 4 pi k into a minus b. So, that is the charge on the whole shell. And now, we will find the field inside and outside. The field is once again radial because of symmetry. The flux through the Gaussian surface of radius r outside the sphere, which must be equal to q by epsilon 0, 4 pi r squared E must be equal to epsilon 0, q by epsilon 0. Q is the total charge, which is 4 pi k a minus b. So, this divided by epsilon 0 is 4 pi r squared E. Therefore, E is k by epsilon 0 a minus b into 1 by r squared for points outside the shell. And once again the field varies as 1 by r squared. Why? Because for a point outside, whole charge is concentrated at the center of the system. For the field inside the shell, we draw a Gaussian surface of radius r. The charge within this sphere I will integrate between b and r, not b and a, but between b and r. And if I integrate that, then I find this charge in this part of the shell, which is inside the Gaussian surface of radius r. So, the charge is 4 pi k integral from b to capital R of dr. So, which is 4 pi k r minus b. Use of Gauss theorem now, 4 pi capital R squared times E is equal to this charge which we have just found divided by epsilon 0, from which we get E is equal to k by epsilon 0 into r minus b by 1 by r squared for a point between b and a, that is inside this thick shell. So, that is the field, and if you can see that if you make r equal to a, then we will get the same result as we did earlier. In this lecture, in fact, in the last 3 lectures, we have been studying flux and Gauss theorem. We have applied Gauss theorem to several situations, but I would emphasize that you remember that when we apply Gauss theorem, then only the charge inside the surface matters, the charge outside the surface does not matter. And we have applied Gauss theorem to several situations, and we have also done several problems based on Gauss theorem, and we found that for consistency everywhere it is the charge inside the surface that matters. So, the Gauss theorem is integral of E dot ds always equal to q by epsilon 0, where q is the charge inside the surface. Now, all these results that we have derived, especially the result that near an infinite sheet of charge or a very large sheet of charge, the field due to this sheet of charge is epsilon sigma by 2 epsilon 0, where sigma by epsilon 0, where sigma is the charge density on this sheet. So, on this sheet we have a charge density sigma, and the field due to this sheet is independent, as long as we are near the sheet, is independent of the distance, and it is equal to sigma by epsilon 0. It is this fact that we shall utilize in deriving the expression for capacity of a capacitor. What is a capacitor and what is a capacity? Capacitor is a system which holds charge, and capacity is the capacity of this system capacitor to hold charge. And now we are entering the area where we shall now talk of currents also. So, it is a current electricity that we are starting, and the first topic in that current electricity is the topic of capacitors, and we shall utilize the results that we have derived so far on the basis of Gauss theorem.